Hello, I'm Adam,
And I'm John.
and today we're doing a proposal on the paper, a supercapacitor-based energy storage system for elevators with soft commutated interface for our ME4622 undergraduate seminar class on July 22nd, 2021. The presentation is laid out in three main categories: the literature survey, the improvement proposal, and the references.
So the first study was titled Understanding Supercapacitors Based on Nanohybrid Materials with Interfacial Conjugation. The second study, Ultracapacitor Modeling and Control Using Discrete Fractional Order State-Space Models. And ultracapacitor is another word for supercapacitor.
The third study we looked at was a new battery/ultracapacitor hybrid energy storage system for electric, hybrid, and plug-in hybrid electric vehicles. The fourth study we looked at was a supercapacitor-based energy storage substation for voltage compensation and weak transportation networks.
For the fifth study, it was charge transfer and storage in nanostructures, and that looked at relevant principles used for lithium-ion and activated carbon capacitors, and they were shown to be valid for other charge conversion agents such as photoelectrochemical and dye-sensitized solar cells. For study 6, it was entitled A Review on Electrochemical Double-Layer Capacitors.
The seventh study we looked at was system integration and powerful management for a series hybrid electric vehicle using supercapacitors and batteries. And then the eighth study was the state of charge, or SOC, balancing control of a battery energy storage system based on a cascade PWM converter. PWM converter is a pulse width modulation converter, which was implemented into renewable energy storage systems in order to smoothen out large fluctuations in power.
The ninth study was for control strategies for battery supercapacitor hybrid energy storage systems. And the 10th study was an overview of dual active bridge isolated bidirectional DC-DC converter for high frequency link power conversion system.
Putting what we learned from all the studies together, we found that there were modeling advances for the supercapacitor systems using the fractional order calculus in order to better model or simulate the systems. There are also a lot of material improvements using hybrid nanomaterials and graphenes in order to increase the capacitance of the system, which resulted from improved stacking at the interface between the two different materials. The reduction in the equipment of size over time due to improvement of technology, as in the DC-DC converters, was seen throughout the studies. And then the combination of both new and old technology, being both in supercapacitors and rechargeable batteries, in order to smoothen the power draw or power demand fluctuations of the systems.
As far as aspects that were not considered, the study didn't go into a lot of different capacitor configurations. They could have incorporated a battery bank, which would further fortify the elevator system against power fluctuations and outages. They could use carbon nanotubes with graphene to increase the capacitance further. And they could also use soft switching solutions that would include soft commutation for rectifier switches and would provide a larger soft switching range than the traditional zero voltage switch or zero current switch.
Looking at how to improve the original study, we can increase the number of supercapacitor system configurations tested, because the original study only tested one or two configurations, but testing more configurations can outline a pattern of increased efficiency between the different setups. You can also expand the study to include the improvements on capacitor design and construction using the new, smaller DC-DC converters or other nanohybrid materials in order to increase the capacitance of the supercapacitive banks. One of the problems in the original study was the lack of having a super strong supercapacitive bank. So a low voltage supercapacitor bank hindered the results of the original study. And these are our references.